Yeah, so the recursive computation of the DTV distance is again obviously in O of 3 to the power of n plus m. Looks very similar to the edit distance, absolutely. So we can also solve the whole thing by using the same dynamic programming scheme as we have experienced in the chapter of the edit distance. So yeah, any path between x and y can be expressed as a path in the x times y matrix using the dynamic programming scheme. So here in the following example, please take a little bit care, attention. In the following example, 0, 0 is the lower left corner. So the blue time series here is displayed from top to the bottom. Yeah, so for the red one here, this one here is 0. The time slot 0, and this is so this is the starting time slot for the blue one here, and this one here is the starting time slot for the red one here. So 0, 0, index 0, 0 is down here, yeah, and not somewhere here or here, like we had. So here we had it before here, yeah. Yeah, and now what we are looking here is we're looking for warping paths from 0, 0 to nm, yeah. And you see here some different warping paths, for example. So this one here is the warping path that represents the Euclidean distance, which is just the one that goes through the diagonal here. And then if we have a little bit more distortions, then yeah, we just yeah, go to the side. So we leave the diagonal, and the more warping we have, the more it is not the diagonal anymore. No? And the dynamic programming scheme now again tries to, so here are of course again the differences between the individual time slots, yeah, and then we try to find a cost minimal path from 0, 0 to nm, or the other way around, with the dynamic programming scheme. Yeah, some properties here. Dynamic time warping is typically not a metric, basically because it allows the replication of elements. Yeah, so here's an example. There's no identity of indiscernibles. Yeah, so the dynamic time warping distance is of this x and this y is 0, even though they are not similar. Yeah, it's just because we can compare this one here with this one here, 0. Then we warp y and stay here with x. So we compare the one here and we compare the one here. So another warping, and then we warp x. We move both. Compare this one here, and then we compare this one here with this one and this one. So the warping path, the cost optimal warping path, will give a cost of 0 for those two, even though they are not identical. Yeah. So this is one thing that should be fulfilled if we're talking about a metric, but it's not here. And there's also no triangle inequality. So here you see x, y, and z. So x is 0, 0, 0, 1, 2, 2, 3, and so on and so on. So we have yeah, x between the distance between x and z is 0, which is not not smaller, yeah, than the distance between. Sorry, there should be no. That's completely bullshit here. So the distance between y and z is 0, obviously. Now I have to rework the whole thing here because this is completely bullshit. The examples is okay, but this is obviously some stupid example here. So the distance between x and y is 1 plus 3 plus 3 plus 3, which is 10. Yeah, now 10. Okay, so a 1 is missing here. So between x and z is 10, and then we have between x and y, that should be x and y, is 2, 4, 7 plus 1 is 8, plus between y and z, which is just 1 here. Yeah, that matches. Then this is a 1. This is a 1, so it should be a 2 actually, but anyway, and this is a match again. Yeah, so in that case, the triangle inequality does not hold. Yeah, okay, so and there's just one comparison that you see that dynamic time warping is different, obviously. So here's a comparison time series that measures the daily network traffic of a company. Yeah, and you see here that we have, for example, in the blue cluster here, we have a normal 5-day week, and then we have a cluster of the green ones here, a 4-day week, and so on and so on. Yeah, so Minkowski will mix it all up again, because it cannot handle this time frame distortions. Yeah, and dynamic time warping is able to do that, even though here in the 4-day working days, 4 working days cluster, we have different working days, different fire target, different days off. So here it's Wednesday, here it's probably Friday again. So it doesn't make a difference here. And here are some 3 working days weeks with different working days. Obviously, no problem for dynamic time warping. Yeah, so this is a nice thing if you want to have that. Again, very application specific, of course. Yeah, and then finally, of course, we also have LCSS, so least common subsequence for time series, which is tolerant to gaps in the two compared time series. Very popular, for example, for trajectories, where you may have some common path in the middle, where both trajectories have to, I don't know, use the same motorway or the same streets to go into the city, but they start from, say, different countryside towns, villages, so one starts, I don't know, from Garching, and one starts from, I don't know, Freising, and then they use the R9 to go, well, that's not the R9, but anyway, to go inside, and then at the end they all want to go to Oettingenstraße, but one finds a parking slot very close to it, and the other finds a parking slot which is a little bit further down. And LCSS now can compute or can at least cover the fact that they have a very long common road here, common route in that case. So LCSS in that case could be a good idea. That was the similarity measures, and next up will be feature extraction.